Okay, so we're going to go on to number 5, which is a question about the binomial distribution. So the first couple of questions are fairly straightforward that we can do on our calculator. So the first one is saying, given that x is distributed binomially, n is 25, p is 0.35, find the probability that x is equal to 12. So that means that we've got exactly 12 households with satellite TV. So let's take a look. We're going to go to menu 7, which is my distributions. Here, because it's x equals, it's probability distribution. So I'm going to do it as a variable. I'm not going to use a list. Now I know that here x equals 12, n equals 25, probability is 0.35, and it gives me an answer of 0.0650. Probability that x is greater than 12, so that means probability that x is 13, 14, 15, all the way up to 25. It's probability that x is greater than 12. Let's just write that down, because we often make mistakes here. 13, 14, 15, all the way up to 25. So the converse of that is that x is anything between 0 and 12, which is x is less than or equal to 12. So it's 1 minus the probability that x is less than or equal to 12. Remembering that it always needs to be less than or equals here. Just remember, less than or equal to 12 means 0, 1, 2, all the way up to 12, which is the converse of what we had over here. So we know they must need to add to 1. So again, going to my distributions menu. This time I'm looking for a binomial cumulative distribution because I've got my less than or equal to, so it's option 1 on the second screen. Variable. In this case, x is still 12, n is 25, p is 0.35, gives me 0.9396. So go back to my main screen, 1 minus 0.9396 gives me an answer of 0.0604. Okay, so for part B, we need to understand the terminology that's using here. So expected value of x is the same as the mean of x. So E of x is equal to, and this is in our formula booklet page, I think 23, the expected value of x is n times p, which is, in this case, n is 25 times 0.35. So 25 times 0.35 gives me 9.75. The variance of x is np, 1 minus p. We've already worked out np was 9.75. 9.75 times 0.65. Which gives us a variance of 5.6875. So the question is, what's the probability that the value of x is between 9.75 minus root 5.6875, so 9.75 minus root of 5.6875. Which is 7.365. And 9.75 plus the square root of 5.6875. Which is 12.135. So the question's really asking us, what's the probability that x is between 7.4 and 12.1? Well, we know that x is discrete, so it can only take whole number values. So this is the same as the probability that x equals 8, 9, 10, 11 or 12. It can only have whole number values. So the easiest way to do this is to find the probability that x is less than or equal to 12 minus everything below 8, so minus the probability that x is less than or equal to 7. And we're going to use our graphics calculators to do that. So I'm going on to binomial CD. I know that x is 12, n in this case was 25, p is 0.35, and it tells me the probability that x is less than 12 equals 0.940. Minus the probability that x is less than or equal to 7, which is 0.306. Gives me an answer of 0.634. Notice that the question here is in fact asking us what's the chance of x being one standard deviation below the mean and one standard deviation above the mean, which in a normal distribution is 66%. So here we've got an answer of 63.4%, so fairly similar to what we would expect in a normal distribution. Okay, so we're going to go on to question part C. So it asks us how many households must there be such that the probability of having at least one household with satellite TV is greater than 99%. So we're going to start this by saying the probability that nobody has satellite must be less than 1%, must be less than 0.01. So if I've got n households, we know that the probability that each one of them doesn't have satellite TV, probability not having satellite, is 1 minus 0.35, which is 0.65. So the probability of any individual household not having satellite TV is 0.65. So if I've got n households, the probability that none of them have satellite TV is 0.65 to the power of n. And we know that 0.65 to the power of n must be less than 0.01. And the question is, how many households do I have to have so that this reduces to less than 0.01? Well, the easiest way to do that is to take logs of both sides. So I can say log, doesn't matter what base, log of 0.65 to the n is less than log of 0.01. Using my rules of logs, I've got n log 0.65 is less than log of 0.01, and so n must be less than log of 0.01 over ln of 0.65. Well, I can already spot that I've made an error here because I know that n has to be a suitably large number, so it's odd to find that n is less than. And the reason why we've made a mistake here is because I've forgotten that when I divide by a negative number, I need to change the inequality sign. If you check on your calculator, ln of 0.65 is going to be a negative number, so I'm going to just change that round. If you'd set this up as an equality rather than an inequality, you wouldn't have this problem. So let's just check on our calculator. I'm going to do the ln of 0.01 divided by ln of 0.65, and it gives me an answer of 10.7. So n is greater than 10.7. It needs to be a whole number of households, so n here, the smallest possible number is going to be 11 households. So looking on to part D, we're going to start this out by setting out our hypotheses. So the null hypothesis is that the probability is what we thought it was before, so it is going to be 0.35. The alternative hypothesis, he believes that it's higher, so the alternative hypothesis is that p is greater than 0.35. So we then test using the null hypothesis and see how likely it was for him to observe and at least as extreme a result as what he saw. So under h0, the probability that he would see as many as 13 or more households. Now, probability that x is greater than or equal to 13 is 1 minus the probability that x is less than or equal to 12. So I can reach for my scientific calculator and find the probability that x is less than or equal to 12 under h0. So x is 12, n is 25, under h0 the probability is 0.35. So that gives me an answer of 0.93940. 1 minus 0.940, which is 0.060. So the chance of seeing a result as extreme as what he saw was 6%. So because 6% is greater than the 1% significance level, there's not enough evidence to reject h0. To reject h0, so that tells us that insufficient reason to believe. Proportion is higher than 35 to 0.35.